Yeah, so my name is Ethan Rudd. I'm from the Sophos data science team, and today I'm going to be sharing this talk, ALOHA, Auxiliary Loss Optimization for Hypothesis Augmentation. This has nothing to do with the ALOHA network protocols, but it's a wonderful acronym and it allows me to get in some nice Hawaiian art throughout the slides. So what's this talk about? Well, at the high level, machine learning malware detectors are typically trained using a single label per example, per malicious example or per benign example with an associated 0-1 label. But there are lots of other labeling sources, labels, other metadata, et cetera, that's really available in existing feeds. And so we'd like to explore how we can use this to create a better malware detector. So in sort of these before and after photos, on the left-hand side here, I have sort of a de facto industry standard of a neural network, of a deep neural network, used for malware classification. For each sample, there's one output, there's one label, and there's one loss function. And this yields actually pretty good detection performance when you train it on the right data. I mean, there are a lot of commercial pipelines that are built on this type of model. However, we can actually do better than this. And so our ALOHA approach here, per each sample, uses many outputs, many labels, and many loss functions. Before I dive into the guts of how ALOHA works, since we have people from all sorts of fields, I wanted to take a minute to review sort of the state of malware detection and where we're at. So up until around 2015, malware detectors were generally signature-driven, with a few exceptions. In around 2015, machine learning for malware detection sort of came around and got into a lot of companies, a lot of pipelines, et cetera. So most of the detectors now are a hybrid of ML and signature approaches. And these can use either static or dynamic features. For this talk, we're focused on detection of static portable executables, but the technique that I'm about to outline could apply to a lot of different malware types. Detection using machine learning for malware is built on binary classifiers. Like deep neural networks, other common approaches use gradient-boosted decision machines with binary outputs. That said, we're going to focus on neural networks throughout this talk. And these detectors are trained on millions to hundreds of millions of labeled samples. The classifiers are also periodically retrained to reflect evolving threat landscapes, so they're not just trained once. New versions are rolled out over and over and over again. And the trained classifiers can be used in a variety of contexts. They can be deployed on customer endpoints or in security operations centers or in the cloud. It doesn't really matter for the purposes of this talk. So as I said, we need millions and millions and millions of labeled samples. So how do we get these labeled samples? Well, a common approach is to use vendor aggregation services or threat intelligence feeds, which take multiple sources for prediction and use those. So a vendor aggregation service, for example, will take all of the vendors throughout the industry, basically, and say, for each malware sample, how are these labeled by all of the vendors? And then, especially as we give some time for blacklists and whitelists to settle down, once we aggregate, we can get a pretty good aggregate label of malicious and benign for each sample. So the way the deep neural network detector works during training is we take some featurization of a malicious or benign sample. We pass that through the network using a forward pass. We get an output score, and then we compare that against the ground truth label using a loss function. We evaluate the loss, and then we update our network so as to minimize that loss. And we do this for lots and lots and lots and lots of samples. So we have a network with learned parameters that work well for classification. When we go to deploy, we simply have to distribute these parameters to whatever our deployment scenario or use case is. And this serves to predict whether a given file on the endpoint or in whatever our use case is malicious or benign. So that's sort of the standard workflow. But as I alluded to earlier, there are actually a lot more labels that we can get, a lot more sources that we can get labels from. With these vendor aggregation services alone, we're actually creating this aggregate label. We have, from the services themselves, individual vendor detections the number of vendor detections, the detection names by vendor at the very least. So can we craft some sort of auxiliary labels and learn from these during the optimization process? Well, the answer is indeed yes, we can. And so how do we do this? Well, it's actually fairly simple. We add additional outputs to our neural network as well as additional loss functions to account for these additional labels, and then we train our network accordingly. This approach has two advantages. One of the advantages is that we can actually prune our auxiliary output paths and prune our associated parameters so that when we go to deploy, we don't actually have to change anything with the deployment infrastructure, and we can nominally get better performance for our detectors. But if we do have the capability of changing our deployment infrastructure, we can also use the auxiliary outputs to deliver additional functionality to the same network that's just been trained once. So for this work, we used the following labeling sources. We used an aggregate malicious and benign label. We used the net number of vendor detections within our feed. We used detections from 9 selected vendors. And then we used malware attributes, malware attribute tags for 11 tags. And these basically describe malicious samples in terms of semantic content. They're binary tags. They're not mutually exclusive. And actually, we derived these and published a paper on these called Semantic Malware Attribute Relevance Tagging, or SMART, which I will refer to you at the end here. But that goes over how the tags were derived. So for every single label, we also have an auxiliary loss function. So for our main loss, we use just a binary cross-entropy loss. For our count loss, we use a Poisson loss. Then for our vendor and tag losses, we use sums over binary cross-entropy losses. Our total loss then becomes the main task malicious benign loss plus a constant times the sum of all of our other losses. So during training, we have multiple output paths, we have multiple labels, and we have multiple loss functions. The losses evaluated by these loss functions are then aggregated, and then we use backpropagation to update all of our parameters. And while I mentioned that we can use the other outputs to do other things, for the purposes of detection alone and for deployment, we do not need to change our infrastructure at all. So deployment looks the exact same as sort of the standard industry use case. We have a neural network which takes in some featureized malicious or benign sample and then does prediction. So I've outlined the technique, but now let's see how it works. So in order to do this, we collected a data set of approximately 9 million training samples with 100,000 validation samples and 7.7 million test samples. Our test data sets consisted of files that were collected temporally after the training data set. So this prevents us from cheating, if you will, during the course of our evaluation. And the featureization scheme that we used was consistent with that derived by Josh Sachs and Konstantin Berlin. The paper referencing that is in the slide. So when we went to compare performance, we fit different combinations of loss functions. We fit networks trained with different combinations of loss functions. And for each of these combinations, we fit 5 runs with random initializations and random mini-batch orderings to get sort of a statistical view of performance. So when we go to analyze performance, we do this via what are called receiving operating characteristics curves, receiver operating characteristics curves, or ROC curves. And for those that might be from slightly different fields, I'll just explain real quick how this works. So on the x-axis, we have a false positive rate. On the y-axis, we have a true positive rate. And basically what these curves are saying is, at what threshold in terms of false positive rate can we deploy and get a detection rate shown by our true positive rate? So the idea is to have the curves further up and to the left. That indicates better performance. But for our use cases specifically, we want to be able to do very, very well at extremely low false positive rates. So the net area under the curve does matter, But what really matters is as we get into the really low FPR region, which is one of the reasons why these curves are on a log scale. So when we add our count loss to our main malware loss, we get a substantial bump in performance, both in terms of the AUC, but also, more importantly, in the relevant region towards low FPRs. When we add our vendor losses, we see sort of the same effect, not quite so much of a bump in terms of area under the curve, but we do see at lower false positive rates, we get actually a more dramatic bump. Similarly for our tags. And then when we combine everything together, we see that we get improved performance even over any of those additional losses, over any one additional loss. We get not only a bump in area under the curve, which seems to be statistically non-negligible, but we also see a dramatic bump in terms of the detection rate at low false positive rates. We also see two modes of improvement. One sort of at around 10 to the negative third to 10 to the negative 2 false positive rate, which we believe is mostly driven by the count loss. And then we see additionally this very low false positive rate improvement, which we believe is mostly driven by these multi-objective binary cross-entropy losses. We further see that we have reduced variance in terms of our overall ROC curve across all of these different initializations, which is also useful. So okay, we see that there are some improvements, but what's really driving these? Is it some strange regularization effect, or is it due to the network's ability to correlate information from all of these labels? Well, to test this, we added some auxiliary loss functions on non-informative targets, that is, targets that don't carry any additional information from the labels that we already have. And what we found is there was no bump whatsoever. So this provides us some evidence that the ALOHA gains come from actual correlations that the network itself is learning between these heterogeneous labeling sources and heterogeneous labels. So we see that adding auxiliary optimization objectives in training does noticeably improve performance of an ML malware detector. It seems to be largely a result of the neural network's ability to correlate information across labels, not a regularization effect. An ALOHA network can be trained and deployed with minimal changes to existing infrastructure, or we can actually use the additional outputs for applications, for novel applications like endpoint detection and response and managed detection and response. So as an example, if we wanted to use the tags to describe not only is the sample malicious or benign, but what type of malware is in this sample for an analyst usage, we could do that with the same network representation. And we'd only have to train it once if we wanted to say an application like that in the cloud or in a SOC, but maybe didn't want to change our deployment infrastructure on the endpoints where we're only doing detection. So before taking Q&A, I just wanted to point you guys towards several derivative works and related research works by both our own group, but also by others as well. So actually, I came across a blog post a few weeks ago by this fellow, Jason Trost, who actually took our ALOHA scheme and employed it for domain generation algorithm detection. It's a very good piece of work. I recommend it. Microsoft Research had a paper called MTNet, which actually did a similar approach to ours. They used two categorical cross-entropy losses, and all of their outputs were softmax outputs. So they had a detection as well as a Microsoft family name prediction. And they also did theirs on dynamic features. So they actually found similar things to what we found. And so it's really cool to see us substantiating their work and them substantiating our work too. The tagging paper that I mentioned, this paper describes the approach that we used for malware tagging. I'm not going to go in too much detail, but I want to steer you guys in that direction in case you're curious about that. This paper, A Mixed Objective Optimization Network, was one that I actually did a few years ago on a vision data set for facial attribute detection. And what's sort of interesting about this is it uses a similar approach for a much, much different data modality. It's very cool to see that this works across a lot of different data modalities. Finally, there's a paper, Learning from Context, that our group put out where We use multi-view learning instead of multi-objective learning, basically turning the ALOHA approach on its head. We could potentially trivially combine this approach with the ALOHA approach. So as I said, I'm with the Sophos data science team. We're a really great team of researchers. We're submitting work to a lot of industry conferences, a lot of academic conferences as well, a lot of great venues. So if you like what you saw, please check us out. Here's our group. And lastly, I'd just like to acknowledge both Sophos for funding this research and promoting it, as well as my co-authors and collaborators. This was really a team effort, and so I want to give them their due credit. And now I guess we have time for a couple questions.
Thanks, Ethan.
Thank you.
You might need this.
Thank you for the presentation. First of all, I want to say I can see a benefit of aggregating the labels. So because it kind of protects against like noise in those individual labels. So my question is, do you think ALOHA makes like life of an attacker who wants to poison your data set easier? Because those small auxiliary loss functions are easier to attack than an aggregate loss function. So if an attacker wants to attack, like poison your data set, attacking those small functions is easier. So what do you think about that?
So that's a good question. I haven't thought a lot about this, but my intuition would actually suggest that it's not necessarily easier, because you have to actually attack, from a data poisoning perspective, you have to attack every single loss function. So you're not just attacking one. If you poison the data and it influences one loss function specifically, it might not influence other loss functions. So it's something that I would have to experiment with to fully answer the question. But my intuition would actually tell me that it would be harder to attack a multi-objective technique than a single objective technique.
Okay, thank you.
Thank you.
Hi, Ethan. Thank you. This is Rajarshi Gupta from Avast. And the very nice work of like looking at different objective functions and different data sources to do it. I was kind of lost in your ROC curves, because while I really appreciate looking at ROC curves with low false positive rates, I mean, at the left end of it, the true positive rates are very, very small. So the part that's really interesting is sort of where you're getting to true positive rates of 95, 100%, and where your false positive rate is around 1%, but over that region, the gains aren't as much.
Yeah, I mean, it's a fair point, and I would point out that the true positive rates, the detection rates, what constitutes a good detection rate varies depending on the context that you'd want to employ your technique. So really, I mean, a better detection rate anywhere is progress, right? Now, what's considered commercially viable, it depends on the application. But even if we're below where we might want to deploy a good detector at a given at a given false positive rate, that might work very, very well for an EDR or an analyst application. So it really depends a lot on the application. But I would say that if you look fairly consistently along this curve, for example, we see quite the gain of greater than, we see a gain over the baseline in pretty much all regions of the curve. So yeah, I mean, I think it's a fair point, though.
Let's thank Ethan. Thank you very much.
Thank you.